Number one, this is one of those problems in real life. The way you solve a problem is called a solution. The solution is usually known as a derivation. Okay, so these problems are not that easy to solve in real life cases. Okay, because you will get an inelastic collision. Collisions are inelastic in real life. Somebody gets hit, obviously momentum is going to get transferred. Aside from that, the kinetic energy is going to be lost. All right, so there's person is going to break bones. There's going to be tremendous amount of heat. There's going to be tremendous amount of sound. Sometimes the person breaks apart. So the real life collisions are inelastic collisions. Okay, so for us to be able to solve problems like this, what we do is we come up with an estimate. Okay, so we have to do an estimate. So we will assume that the collision is elastic. So you will have to look at momentum before impact. So this is the car, this is the person. The car is coming at this person at 3 miles per hour. And then we'll check to see what happens after impact. This vehicle is going to lose some of its speed, and the person is going to fly off. In reality, this person's speed is going to be double that speed, but it doesn't matter. I'm setting up for derivation. That's what it calls. All right, so the question is, what's the speed of the car and what's the speed of the person after impact? Okay, so speed of the person is going to be almost double the speed of the car. The speed of the car is going to be slightly less than the initial speed of the car. So that's what we should get if it's done correctly. Okay. Normally, something like this, if it's an in-person lecture, if I had to do it on a projector or whatever, something like this would take probably an entire lecture time. Okay. Details aren't that important for you guys because I'm not going to ask you about the derivation, but I'm interested in the conceptual understanding of what goes on. Okay. So initial momentum is, so you're looking at the total momentum of the system. So the system composed of two masses. Only this one is moving, the second one is not moving. So the initial momentum is going to be composed of the first mass moving at this speed. The second mass is not moving, so it's not going to have any momentum. The final momentum is going to be composed of this mass moving, so this mass is going to have momentum, so it's this one. So add up the momenta of each and every single mass. Cute. All right, so total momentum before and after collision is going to be the same. So momentum is conserved. So we end up getting an equation like that. Assume that this is an elastic collision. We were looking for the speed of the first and the second mass after impact. Assuming that this is an elastic collision, which means that kinetic energy is also going to be conserved. So kinetic energy is related to speed, obviously. So the kinetic energy of total kinetic energy of the system after and before will be the same. So this is the total kinetic energy of the system after. This is the total kinetic energy of the system before. All right, and we got two unknowns, which means that you need to have two equations. This is your equation number one. This is your equation number two. Oh my God, this is so awesome. Okay, so you got two unknowns, two equations. And then how do we solve this problem? Okay, this is where it gets kind of fun. All right. All right, you notice that you got 1/2 on both sides and just get rid of that. Okay, and then just clean up the equation. All right, I'm gonna move my mass number one to the left, mass number two to the right. Okay, so we are just at this point we're trying to get it into a form that we can actually utilize it. All right, so this is the change in velocity square of the speed of mass number one, and you got mass number two, speed of the mass number two, mass and the speed. Okay, so obviously mass is the common term here, so you can just factor it out. All right, so this expression that you're looking at, all right, square of the first impression minus the square of the second impression, is a mathematical identity. You can express it like this. This is kind of cute. All right, if you remember it, awesome. If you don't remember it, it's not a big deal for now. Okay, so this term is going to get expressed like that. All right, so once you put it in that form, now you can start combining equations. All right, so which means that I'm going to play with that. All right, so I'm going to take this equation in the gray, and then I'm going to use this equation. So we will do some kind of weird substitution. All right, so you got two unknowns, so you need to have two equations for that. So this is equation number one. This is equation number two. All right, you got your M1 here. Okay, you got your M2 here. All right, so I will do the same here. I'm going to collect my M1 on the left-hand side, M2 on the right-hand side. I'm going to make these two equations look the same, more or less. All right, so the mass number one is going to be here. This should be mass number one. Mass number two is going to be there. Okay, I made a correction. I factor out mass number one. I want to make this great equation number two. Okay, so masses are collected under mass number twos are on the right-hand side, mass number ones are on the left-hand side. All right, so I need to simplify the equation. Okay, so let's try to simplify this one. What we can do is we can get rid of this term because both of them have the same term. How do you do that? You take this and divide it by that. Okay, so if you wonder what we do most of the time in physics, this is the sort of stuff that we do most of the time whenever you come up with a concept. You just a lot of manipulations. All right, so this equation is divided by that equation. So what do they have in common? Okay, M1 is in common. and the change in velocity is in common on the left-hand side. Okay, all right, so let's just turn it into an equation first. All right, so this side is going to be divided by that side. This term is going to be divided by that term. Okay, now for the common terms, m1 is common, m2 is common, negative divided by negative. All right, v minus 1. Okay, so change in velocity for the first mass is going to be in common. All right, so just cancel out those. On the right-hand side, the masses will cancel, the negatives will cancel. Oh, we're making some progress. All right, and then this gives us an equation. It's my green equation. This is awesome. All right, what did we come up with? Guys, the only thing we did, we came up with a very simplified equation. We can express the second speed in terms of the initial and the final speeds of the first mass. Okay, so we know the speed of the person or object getting hit, and the speed of the object getting hit is a combination of the initial and the final speeds of the object responsible for the collision. All right, let's translate it in English. This is the person who's getting hit right after an accident. So the person's speed is going to be initial speed of the car, which is 30 miles per hour, and plus the final speed of the car, that's probably going to be still 30 miles per hour. So that's going to be about 60 miles per hour. So conceptually, that's where we are at. Mathematics is still incomplete. So, which means that we have to come up with an expression for the individual speeds. So we're still interested in V1 and V2. So we can pick one of these formulas and check to see which one is easier to use. This one is easier to use because it doesn't have a square in it. All right, so what I'm going to do is I'm going to just substitute this in there and now solve for V1. Okay, so that's something that we could do, I suppose. Yeah, so V2, substitute V2 in there. So when you substitute V2 in there, so this V2 here is going to look like V1 plus V01. And then obviously get rid of the parentheses. And then everything is going to go dark. That's a near-death experience that you guys are having. Hold all the terms to the left. All right, so this is the initial speed of the vehicle. And this is the final speed of the vehicle on the left. The green ones are the initial speed, the blue ones are the final speeds of the vehicle. So factor out the like terms. We're almost done. Okay, move that term to the right across the equation. So it's going to take a negative in front of it. And then isolate V1. All right, so if you distribute the negative, okay, M2 is going to have negative in front of it. Negative times negative is going to be positive. So I just changed that side of the equation a little bit. And then isolate V1. This is the speed of the vehicle, final speed of the vehicle, expressed in terms of its initial speed. Cute. Now I know what happens to the vehicle. I know what the final speed of the vehicle is going to be. All right, so here's the mass of the vehicle. Here's the mass of the person, divided by the total mass of the system times the initial speed of the vehicle. All right, so this is called a solution. Now I got a mathematical expression for the first speed. Okay, I don't expect to be able to do this sort of stuff at this level. I'm just doing it just for the hell of it, because I would normally spend an hour doing this sort of stuff, but I'm going to quickly go over it because there's a couple of things that I want you to know. Number one, we're getting an estimate. We're assuming that it's an inelastic collision. We got two unknowns, which means that you need to have two equations, and then it's going to give you the speed. This is from the formula sheet. So this equation is going to be available to you, okay, for problem solving purposes. So this is the initial speed of the vehicle that you're looking at, and here's the final speed of the vehicle. This is the initial speed of mass A. This is the final speed of mass A. So you're looking at the differences in mass. Okay, so that's how the equation, the actual physics is done in real life, believe it or not. The next thing is, now let's figure out the speed of the object, the final speed of the object, the person getting hit. Notice that we came up with an expression for this one. We already know the initial speed of the car. So the expression that we came up with here is going to get substituted into this equation. It's going to give us V2. All right, and that's what we will do. So this gets substituted in right there. Okay, I'm just going to rewrite the equation so that V2 is going to be on the left-hand side. And it's playtime. Just edit. Okay, so you add them up. All right, so notice that on the right-hand side, you have common speed. This is the speed of the vehicle. So how do you add them together? Okay, so it's kind of a math trick that goes into this sort of stuff. What I'm going to do is I'm going to keep this expression the same. And then for us to be able to add these two up, you need to have a common denominator. So what I'm going to do is I'm going to multiply and divide this expression by the denominator, which is this. All right, now notice that the initial speed is going to be a common term, so I'm going to factor that out of the algebra. Notice that the mass of the vehicle from the top is, okay, mass of the person from the top is going to cancel. So 2 times the mass of the vehicle divided by the total mass. Multiplied by the initial speed of the car, okay, and then once again, you go to the formula sheet. All right, and then from the formula sheet, you just pull out the formula. Okay, I just want to go back to that formula. I killed it. All right, let's just finish this up and then go to the formula sheet and pull the formula up. All right, so the formula is this one. Okay, again, this is the mass of the A. All right, so this is the mass of the first object. This is the car. This is the total mass. This is the initial speed of the car that you're looking at. All right, so this is called the derivation. This is how we get to concepts, how we come up with these complicated formulas. Okay, I wanted you to just at least experience a one real problem the way we do it. This is a complicated problem. So this comes out of the conservation of energy and momentum principle. Assuming that it's an elastic collision. Okay, you can come up with a really good estimate. You'll come up with a really good estimate. So question is, when you apply it to real life, what do we come up with? This is the problem that we were looking at. So the person is going to get hit by a car is going at 30 miles per hour. Right, so bigger mass, the smaller mass, the car is moving at 30. The person is not moving. And after impact, what's going to happen is the car is going to move almost at the same speed, slow down a little bit. And the person's speed is going to be nearly twice the speed of the vehicle. All right, so that's what we expect to see. And let's check to see if that's what we will get to see. All right, so mass of the car, the person's mass, the person is 150 pounds give and take. The car is moving at 30 miles per hour. Mass of the car, this is about 5,000 pounds. All right, so what's the speed of the car after impact and what's the speed of the person after impact? Okay, so we had a little bit of, we got two predictions. The car is going to move nearly the same speed, maybe about 28 to 29 miles per hour. The person is going to move nearly double the speed of the car, right? So that's what we expect if the collision is elastic. All right, so we do the conversions. All right, boom, boom, boom. All right, so here's the first formula. This is going to give us the speed of the car. Here's the initial speed of the car. This is the final speed of the car. All right, and we got the numbers, so put the numbers in. And we end up getting about 14 meters per second. This is going to be about 27 to 28 miles per hour. I think it's about 28 miles per hour. So the car's speed goes down by about 2 miles per hour. So that's, in real life, it would be about 26 to 27. So we end up getting 28. That's not bad. Okay, now let's take a look at the speed of the person. We choose the speed of the person. All right, so here's the mass of the vehicle, the total mass, and here's the initial speed of the vehicle. So when you plug the numbers in, it's about 26 meters per second. So this is going to be very nearly double the speed of the vehicle. It's going to be almost 60 miles per hour, but not quite. It's 58 miles per hour. Okay, almost double the speed of the car. All right, so it's going to be 58 miles per hour. It's an elastic collision. If it is an elastic collision, this is what you end up getting. So it's almost agrees with what I just said. Okay. All right, so now we made the assumption that this was an elastic collision. Real life is an elastic collision. So what's going to happen is person's bones will break this and that. So it's not going to be 58 miles per hour. It's probably going to be close to 55 miles per hour. The vehicle speed is not going to be 28. It's probably going to be 26 to 27 miles per hour. Okay, so now you can make some adjustments. All right, so we figured out the speed. So how much the momentum change, how much the momentum changes for the person, and how much does the momentum change for the car. Guys, listen, okay, conceptually. And change of momentum for a system is going to be 0. All right, so net momentum before and after impact is going to be the same. So the change of momentum of the car is going to be the same as the change of momentum of the person. That's what it means. All right, so which means that the motion is going to get transferred to the person. All right, so the motion loss, the momentum lost by the vehicle is going to become the momentum of the person. So momentum gets transferred. That's what it means. So the change of momentum of the person is related to how much the velocity of the person changes within that duration. All right, so initial speed of the person was 0, so we know what the final speed of the person is, so you plug the numbers in. So this is the amount of momentum that the person, change of momentum that the person undergoes. And when you do it numerically, if you're looking at the change of momentum of the car, and when you plug the numbers in, we're going to end up getting the same change of momentum for that. All right, so the momentum that this person gains is going to be the momentum that the car loses in this case. And then the total change of momentum of the system is going to be 0 as a result.